when we talk about the kinetic theory of matter, this is kinetic theory of matter, right? Isn't it? This is kinetic theory of matter. Kinetic theory of matter tells what? That in solids, the particles are arranged in a lattice structure, right? Fixed pattern or lattice
Yeah.
structure, right? Strong forces of attraction, they held their position together, right? The only movement they are having what is tiny to and fro vibrations, right? Isn't it? Tiny to and fro vibrations which are there, right? Did you get my point, right? So this is very important that when we talk about when we talk about the part called as what, when we talk about the part called as kinetic theory of matter, right? We are seeing that the solids are what, the solids will be there arranged. The particles are arranged in a fixed pattern or lattice structure, right? Strong
Yeah.
forces of attraction, they hold together, right? Second, they cannot leave their positions, right? This is very important. They cannot leave their positions, right? And the only movement they are having, what? The only movement they are having is tiny to and fro vibrations. Agreed? This is clear to you, right?
Yeah.
Now, what happens when we give heat? When we give heat to this solid, what happens? The particles, they start to vibrate, right? Hmm. And what happens? The interparticular force of attraction gets weakened, right? Isn't it?
Yeah.
Weakened. You have told me interparticular force of attraction gets weakened. And what happens? That lattice structure is grown because the interparticular force of attraction is very strong over here, right? It's like a cement on the cement wall, right? In the cement wall, on the brick wall, right? It's like the cement. Interparticular force of attraction is very strong. When we heat the solid, what happens? The particles, they start to vibrate, vibrate. And what happens? The interparticular force of attraction gets weakened, right? Clear? Weakened. Understood? Clear? Interparticular force of attraction weakened, and the solid and the lattice structure crumbles. And still the
Yeah.
particles are close together, but they are having movement now. See, in a solid, what happens? You have got tiny to and fro vibration, only tiny to and vibrations. But if you see that when we are heating it, right, what happens? The the particles are now having sliding motion, right? Rolling motion. Two motions are added, right? Again, I'm heating it. When you heat it, what happens? The heat energy is getting converted to kinetic energy, right? And kinetic energy will be increased, right? What is kinetic energy? Kinetic energy which is there for due to motion, right? So they start to vibrate more. Understood? Vibrate more, right? Vibrate more, right? Vibrate more, right? They start to vibrate more and more and more. And this does what? This completely breaks the interparticular force of attraction, right? The interparticular force of attraction are completely broken. Understood this part? Fine. Completely broken. Did you get my point, right? The interparticular force of attraction are completely broken. They are completely broken. And see, the particles are not having any interparticular force of attraction, right? This particular drawing is just for your observation, but the particles are not closed like this, right? If you see the solid, we cannot means this is the thing we have to see that I have zoomed in million sometimes. The particles of the gases are like this, right? Even this is million times zoomed in, right? Isn't it? They are having what? They are having no interparticular force of attraction, right? Isn't it? And thus they are what? They're going from one direction to another direction, right? And colliding against each other and bouncing off in all directions, right? Clear? Did you get my point, right? Now over here we have to understand that when I say that the particles, right? The particles will not have any interparticular force of attraction. This is the kinetic theory of matter we are discussing, right? Kinetic theory of matter. In the kinetic theory of matter, what happens? The interparticular force of attraction are not there, negligible, not there, right? Second, second thing we have to observe is that the particles, the size of the particles, the volume occupied the particles are negligible in comparison to the total volume of the gas. Did you understand the second part which I discussed? The volume of the particles, right? The volume of the particles, gas particles. What's the volume of the gas? Can you guide me quickly? Mine. This is the total volume of the gas, right? Isn't it? Did you get my point? Can you hear me? Can you hear me?
Yeah. So I can hear you.
Is it clear? This is the total volume of the gas, isn't it? And this is the volume of the particles of the gas. Understood? Isn't it clear to you? Right? And how? What's the gas pressure? Can you tell me? What do you mean by what do you mean by a pressure of a gas? Right? What do you mean by a pressure of a gas? Please guide me.
So how much like space it's inside? Like
No, how
how
much
much?
force by which this particle is colliding with the walls of the container? Understood? Force per unit. How much force is colliding with the walls of the container? Did you get my point? Right? Understood this part, right? Hmm? Did you understand this part? What I'm saying? Right? Hello? Can you hear me? When can you hear me?
I agree.
You understood this part? Huh? What I'm saying? Did you understand this part, mine? The what's the pressure of a gas? The particles are having no interparticular force of attraction, right? Nothing. No interparticular force of attraction. They are just colliding on the walls of the container, right? Isn't it? And this will be giving you the pressure. The pressure is what? The force per unit area by which the particles are banging to the walls of the container. Isn't it? They have got no interparticular force of attraction. No forces holding together, right? They're colliding with each other and bouncing off in all directions. Clear? Now tell me one thing. If we increase the heat, will the kinetic energy increase of the gas? Right? Can you tell me if we increase the temperature, when you
Yes, the
increase the
kind
temperature, what happens? Tell me. If you increase the temperature,
kinetic.
the kinetic energy increases. So they will be banging to the walls of the container with more force or less force or the same force. Can you guide me? Hmm? You answer my point. What I'm saying? Will they collide with the walls of the container with more force or less force or what? Hmm? Mine? Mine? Can you guide me? Mine? When you
So
increase the
with more
temperature,
force, more force.
more kinetic energy, more force, and the pressure increases. Understood? The temperature, if
Yeah.
you increase, the kinetic energy also increases, right? And the pressure of the gas increases. Did you get my point? So this is called as an ideal gas. Ideal gas picture we have drawn, right? That what is ideal gas? Ideal gas is a gas where the interparticular force of attraction is not there, right? The volume of the particles, right, is negligible. Gas particle negligible to the total volume of the gas. Did you understand the second part? The interparticular force of attraction are not there. Is it clear to you? Did you get my point? And the total volume of the particles, gas particles, is negligible, approximately zero, in comparison to the total volume of the gas. Did you get my point? Hmm? Did you get my
Yes.
point? This point is clear. Any questions? Please guide me. Understood this part? Fine.
Yes.
Now see, now if you see, when we talk about this, right? So we have to know that this is the picture of the gas, right? Ideal gas, right? So ideal gas will be guided by what? The gas laws, isn't it? By the gas laws. Can you do one thing? Can you see whatever pictures you are posting on the exam resource group, right? You have to go through them before your exam. Can you
Yes.
do one thing? The ideal gas is bound by what? Three laws. What are the three laws? Boyle's law, Charles' law, and Gay-Lussac's law. Is it clear? The three laws,
Yeah.
right? What the first law tells you? If you increase the pressure, the volume of the gas decreases, right? Is it clear? So pressure will be equal to constant into 1 by V. Understood? Did you get my point, right? Is it clear to you? So if I plot P by 1 by V, you'll be getting a straight line like this. Agreed? Agreed? Now, if I
Yeah.
plot pressure with volume, it is inversely proportional. So we'll be getting a graph like this. Agreed? Fine. Got it? Now if I plot, suppose if I plot um, a pressure into volume is equal to a constant. This thing I can rearrange. Understood? If I plot pressure into multiplied by the volume versus volume or pressure, right, we'll be getting a straight line. Understood? Clear? Agreed? Did you get my point? We'll be getting a straight line. Did you get my point, Mahin? Understood? We'll be getting a straight line. Agreed?
Yes.
Fine.
Yeah.
You get my point? So this is a very important part we have to understand. We'll be getting a straight line, right? Agreed? This is clear? So these three graphs, please take a screenshot, please. Take a screenshot and post it, right? Mine, please take a screenshot and post it.
Take it.
P2 V2 by T2, right? P2 V2 by T2, right? Mine, you just update what are the chapters I'm doing, right? Can you update in the Excel sheet? What are the chapters name I'm doing? Hmm? Send me a message, please. Update the chapters I'm doing, content I'm doing. Please send me a message, please. Yeah,
Yes.
please update it because after 3 4 days, of 7 days or 8 days, I will be forgetting. We will be forgetting, right?
Yeah.
Contents, can you update, huh? Okay, please, huh? Do you get my point? Now over here, now we have seen that if we see that when we talk about the real gases, right? We just understood that what are the ideal gases? Ideal gases are those which follow ideal gas equation. What is the ideal gas equation? PV equal to nRT. Is it clear? This ideal gas equation. And can you tell me that what are the important constituents of this ideal gas equation? Can you quickly tell me? Tell
Uh,
me.
Pressure,
What did I tell you?
volume, number of
The
molecules, eight.
interparticular forces of attraction are
Yeah,
zero. They are not there.
zero.
No, there's no interparticular force of attraction between the particles. But
Yeah,
we will be seeing that there is interparticular force of attraction which is there. Understood? It's not that the interparticular forces of attraction are not there, but there are interparticular forces of attraction which are there. Agreed? You get my point, right? Understood? Hmm? Okay. So this is a very important part. Second, what did I tell you? What did I tell you? Tell me. The volume of the particles, the total volume of the particles, tell me, is approximately negligible. It's equal to zero in comparison to the total volume of the gas. Is it clear? Is it clear to you? Understood? Do you understand this thing? The particles of the gas, these are the particles of the gas. The particles of the gas are almost negligible, right? The volume of the particles of the gas is almost negligible in comparison to the total volume of the gas. Is it clear? Did you get my point, right? Understand this part,
yes,
right? So this is a very important point we have to think about. Now, second is that if you see that when we see about the real gases, right? Sorry, the ideal gases. So PV equal to nRT. Now we can rearrange and write PV by RT is equal to N. Is it clear to you?
yeah,
Understood this thing? Now, if I take 1 mole of a gas, right, what will the equation be? PV by RT is equal to 1. Agreed? Do you get my point, right? PV by RT equal to 1. Did you get my point, right? Mine? Understood this part? PV by RT equal to 1. Agreed?
yeah,
Mine? This is clear
yeah,
to you? So this is a very important part we have to know that if we see that when we talk about the when you talk about the ideal gases, right? The ideal gas will be having following the ideal gas equation. Now, if we take 1 mole of a gas, right, then PV by RT with respect to pressure will be a straight line, huh, at around 1. Is it clear? Understood? This is simple maths, right? PV by RT is equal to 1. So PV
yeah,
by RT into you are taking the pressure, it will be a straight line at around 1 because we have taken 1 mole of the gas. Is it clear? Did you understand this thing? Mine, do you know what? I can draw a real life example. Do you know what?
yeah,
Do you know what our parents tell us? That okay, do you know that my friend's son, he tops in school for all subjects? Have you seen?
yeah,
There's no person like this, right? They want to motivate us. That I understood. And they
yeah,
say that okay, do you know what? My friends, my office colleague's friend, Mr. John, his son tops in the school. Huh? His
yeah,
son is actually topping in his cricket. Third,
yeah,
he's a brilliant Spanish guitarist. He performs in the concerts, isn't it? and
yeah,
and he came first in the maths particular exam of the globe, right? Olympiad. Did they
yeah,
say like this? But this is not actual. Actually, it's a frictional case which they want to tell us to motivate us. Understood? Clear? This
yeah,
is an ideal boy that he's topping in his school in all subjects. He's actually topping in his cricket, right? He's a part of the cricket team. He's the captain of the cricket team. He plays good Spanish and he go to concerts. But this is ideal boy which they tell stories about. Understood what I'm saying? Understood? So similarly we have got an ideal gas, right? Ideal gas is a what is an assumption, isn't it? Ideal gas is an assumption. Can we understand that the particles don't have interparticular force of attraction? No, they will be having an interparticular force of attraction, right? However small it will be, right? They will be having interparticular force of attraction. Second, does the particles will be having negligible volume? No, they will be having some volume. Is it clear? Did you get my point, right? Those are called as real gases. Actually in the gases, they have some interparticular force of attraction. They have some volume which is there, right, of the particles. Did you get my point? Understood this part, right? Isn't it clear? So they will be having. Now going to this thing, now we have to understand that. Then can we find out that will real gas behave like ideal gases? Under what conditions will they behave? Understood? Clear what I'm saying? What is the ideal
yeah,
gas? Ideal gases have got no interparticular force of attraction. They will be having the volume of the particles will be having negligible in comparison to total volume of the gas. But this is not the fact. They will be having an interparticular force of attraction. They will be having some volume contribution. So can we see that under which conditions of pressure and temperature can a real gas behave as ideal gas? You might be wondering that why have we taken ideal gases, right? Why have we taken? We have taken ideal gases because the equation is simpler, right? We can use this simpler equation, right? Otherwise, if we want to correct the attraction due to interparticular force of attraction or due to the volume which is there, the equation will be much more complicated like this. Can you see this? This is actual equation. It should be. Is it clear? Did you get this thing? It will be very complicated, right? Isn't it? We have to do quicker equations. So that's the reason we are taking ideal gas equation of this. Clear? Did you get my point, right? Understood. Now we have to think that under what conditions does ideal gases, sorry, real gases will be behaving like ideal gases under what conditions?
Yeah.
The first condition we come across that we plot the graph. We plot the graph of different gases we have taken. Hmm. Suppose gas we have taken. We are doing plotting the graph of PV by RT, right? PV by RT by taking 1 mole of that of the real gas, and we are increasing the temperature and following the curve. Did you understand this thing? At 200 Kelvin, the graph will be something like this. Is it clear? We are plotting what? Tell me. PV by RT by pressure, and we have taken 1 mole of the gas. We are increasing the temperature. See,
Yeah.
understood? And we know that if a ideal gas is that, it will be a straight line. Got it? Understood this part, right? It will be a straight line. Is it clear? You get my point? It will be a straight line like this. Now here is a very important here is the important part you have to understand that whenever we are seeing this particular particular temperature, right? Can we see that at what temperatures does the real gases behave as an ideal gas? What do you think? Which graph is more closer to this graph? This which graph? Tell me. We have taken the
Uh,
real gas and I'm increasing the temperature. See, and plotting PV by RT by pressure. We have taken 1 mole of the gas. Can you tell me
the
at which
1000.
we can tell that at a very high temperature, right? At a very high temperature, right? At a very high temperature, what happens? The real gases will be almost, see, in this zone, right? Almost similar to the ideal gases. Is it clear? Now, to understand that, that the greatest deviation we are seeing, what? The greatest deviation is that at a lower temperature, right? Now, at a higher temperature, what happens? Mine. At a higher temperature, the kinetic energy is more. Understood? So the particles are much more apart from each other. Understood? Clear? Do you get my point? That why it is behaving at a high temperature? Because at a higher temperature, what happens? The particles of the gas, right? Is it clear to you, right? If you see that
Yeah.
at a high temperature, right? What happens? That the particles of the gas are having greater kinetic energy, and they will be spread apart, far away. Is it clear? So if they spread it apart far away, what will the interparticular attraction be? Tell me, if the particles of the gas are very close together and the particles of gas are forced to stay apart, where will the interparticular force of attraction be? More? A or B?
In A.
A, understood. So at high temperature, what happens? The particles of the gas are spread apart, very far apart. Understood? This is clear to you? Are very far apart. Do you get my point, right?
Yeah.
Understood this part? They're very far apart. And thus, what happens? There is no interparticular force of attraction, right? Clear? Understood?
Yeah.
When you decrease the temperature, what happens? Kinetic energy decreases. And the particles will be slowly moving and come closer. And then the interparticular force of attraction can exhibit. Understood? Do you
Yes,
understand
sir.
this thing? We have to see that the interparticular force of attraction has zero. Second, the interparticular forces of attraction will be maximum when the temperature decreases, right? Now see, now can we find out that at what pressure the ideal gases, real gases behave as an ideal gas? Can you tell me? Can you tell me which pressure? Can you see from the graph? This is the pressure we are increasing. See,
Yeah. So 9
it's
times 10 to
at what pressures? At low pressure or high pressures?
low pressure.
Low pressure. Can you tell me why? Why at low pressure the real gases will be behaving as ideal gas? Can you tell me? Can you tell me one thing? If we increase the pressure, what happens? What happens to the particles of the gas? I'm increasing the pressure, right? See, by a piston.
And the intermolecular forces also increase because they're closer
Why,
to each
why,
other.
why, why? First, you tell that
Because they're
what happens to
closer
the
to each other.
particles? Are the particles coming closer to each other or farther apart?
Closer to each other.
Closer to each other. When the particles are coming closer to each other, what happens? The interparticular force of attraction will now be able to exhibit. Is it clear? And that we do not want, because ideal gases do not have interparticular force of attraction. Understood? Did you understand this part? Understood this part? You get my point? That we are seeing that at very high temperatures and at very low pressures. Very low pressure means what? You're pulling the piston up, right? Up, right? And the particles are far away. Understood? Did you get my point? Is it clear?
Yeah.
So the real gases will behave as ideal gases at which conditions? Tell me. At very high temperatures, right? Isn't it? And tell me, at very low pressures. Understood? This is clear to
Yeah.
you. Understood this part, right? Hmm?
Yeah.
Understood. So this is a very important part we have to nurture, right? Fine.
Yes, sir.
Is it clear?
Yes.
Okay, is it clear to you?
Clear.
Is it clear? Just 1 minute, just 1 minute. Please tell me what we discussed. Please tell me that the real gases will be behaving as the ideal gases under which particular conditions? Mind? Please guide me. Bolo. Under very high temperatures, mind, isn't it? First. Second is what? Tell me. Under what conditions? Bolo, mind. Tell me. Mind.
So,
Mind.
and low pressure.
Very low pressure, not low, very low pressure, isn't it? Fine. At very low pressure, what happens? Tell me. The particles of the gas will be moving farthest apart. वही चीज है, हाँ? And the interparticular force of attraction is not there. The volume of the gas is more, and the volume contribution of the particles is negligible. ठीक है, Mahin? Understood this part? Understood, Mahin? Do you understand this part? Mahin, can you read out this quickly? Did you have the question? This part? Mine, can you do one thing? Can you copy paste this, cut paste this over here? Just 1 minute, mine. Can you cut paste this? Wait, mine. I don't hear. Mine. Hmm. Hmm. Have you done?
Just cut it.
What my intention? Whatever then the exam research, you have to go through them. Prior to exams. Right, mine? Understood. Mine. Before I forget, it's just 1 minute. This is page number 38. Kinetics is what? Kinetics is page number 300, right? Mine, can you help me? Just cut paste this graph. This rhyme you understand, huh? The rhyme I told you what? CTRC, huh? ये rhyme. Just to write down CTRC, huh? Just cut paste over here, right? This part, huh? Fine. Quickly. Done?
Yes, I'm just doing.
Done?
So can I have a minute?
Yeah. Let's do one thing. Please read it. Please read it loudly. Loudly. Mine.
Yes.
Have you read it? Read
Yes,
it
I have.
loudly.
So we can draw the following conclusions from
Please read like this. Now we can draw the following conclusion from the graph. The gas behave most like an ideal gas at low
gas at low
pressures.
shows the greatest deviation at high pressure.
Mhm.
The
It,
gas behaves most like an ideal gas at high temperature and shows the greatest deviation at low temperature.
hmm, isn't it? So
Yes.
independent filtering, it will be very helpful to question the validity of two assumptions which we made in the ideal gas. Huh? What are the assumptions? Volume of the particles is negligible. There's no attractive force between the particles, right? Is it clear? Done? So this we conclude what? This we conclude the ideal gas equations, right? That what is the difference between the real gas and the ideal gas, right? Clear? Fine. Now tell me which